Imagine being able to.
Yo, what's up, YouTube? It's your boy JOSHABRAHAM. Yine. My files. My files. Infrared spectroscopy. Okay, that's what IR spectrum is. Infrared spectroscopy. I got it. I got it. Dude, this website is amazing. But what are the common. Let me wash my hands. It feels so oily. So alcohols and carboxylic acids have not broad, very broad. Let me. Organic chemistry. Okay. I think I should release the notes that I used to study. It's not like for people to use. I mean, you could check it out, but it's gonna be useful for me. Organic chemistry, IR, spectroscopy. It's form of graph or fingerprint on how your molecules bonds interact with infrared light. By analyzing it, you can figure out what functional groups the molecule contains. By analyzing it, you could figure out what functional group the molecule contains. The molecule contains and the graph basically my hands are so I wash my hands and it's clean and dry. Because it's clean and dry, my hands stick to the screen, which is so weird. I can't write properly. I have to take my hands off the screen every time I need to write. It is not that hard, but hey, I wish it wasn't there. What can I do to make it more on my skin? Yep, that makes a difference. The graph basically for infrared spectroscopy, x-axis wave number per centimeter, the frequency of IR light related to bond vibration. And y-axis transmittance percentage or absorbance. How much IR light passes through the sample or how much is absorbed. How much IR light passes through the sample or how much is absorbed. Okay, the x-axis contains the wave number and the y-axis contains the rate of absorption or absorption. How do you read it? Each dip peak in absorption. Mm-hmm. Now let's see at the where can I see these peaks for different functional different functional groups. Okay, there might be one in my notes. There's an easy way to get the notes. Dude, that's a lot of lecture slides. What the Okay, I think this is the spectroscopy one. Oh Lord. Determining the structures by spectroscopy, X-ray diffraction, UVVI spectroscopy, IR spectroscopy, mass spectroscopy, determining this UVVV. I haven't. Okay, let's first look into the IR spectroscopy. Is there a page number? No. The mid-infrared approximately for can be used to study functional vibrations and associated rotational vibration structural elements. Determining structures by spectroscopy. Functional groups, region, fingerprint region. The whole thing is in this. Oh, okay. So the alcohol would be this one, the OH, right? Believe the alcohol is 3,200. Yeah, the last one is alcohol. One before that, I don't know. Mass spectroscopy. Okay. Yeah, I just write this. We forgot one important thing. The music. 1650 to 165. Ah, 1550. Dude, the numbers are so fucked up. Medium. That's the cyclic structure. That's benzene. It's a benzino. strong. Okay, the lower the wavelength, the stronger the intensity. No? Nope. Wood 0 strong. CN. Medium. That's alcohol. For alcohol, it's 3,650. That's a fucking big number. To 2,500. Strong, very broad. Very broad. Medium. Broad. Okay, so these are the values. C triple bond N 2,260 to 2,200. C triple bond. Nitrile. Cyano group or nitrile. I knew it was alkyne. What a fucking idiot. Alkene. Imine. Okay. Imine. C double bond O. It's ketone, right? Carbonyl. Okay, there's no specific name for those. Okay. It's a fingerprint region, okay. That was in 700. Mhm. 1550, that would be imine nitro group. 1700 and 2500. Yeah, the second one is carboxylic acid. So that's there. Mm-hmm. It's different. It's different. The fuck happened? How are I forget how this worked. The following spectra is for what are the peaks that you can I so methanol CH T3OH, okay. Nitriles C triple bond N range from 2260 to 2220, 2200, 2200, 2200 to 2100. Alkene 1600, 600, 1600. Imine what is this? What is the last part? Identifying the peaking provided spectrum. Antibiotic structure analysis. There's no four. Following spectrum is NMR spectrum. Well, it's time to look for NMR spectrum, but I'm so confused. Like, if we reach NMR spectrum now, what else? What else is there? Bicrystalline structure elucidation using one NMR spectroscopy. Okay, that's an NMR. I guess that's fucking NMR. That's the same fucking thing. SN1. Okay, that now that's SN1. Main product is propane. Now that those are reaction. Okay, the mechanism. Okay, it's the name of the mechanism. Fucking hell. Lot of shit. I don't think I'll pass the exam. Exercise 4, exercise 5. Exercise 6. Let me check my dates. Cause fuck, that's a lot of fucking exam. Mm-hmm. Mm-hmm. I don't need to do that. Organic, okay. Physics, lab course, exercise. Ah, fucking hell. I took the right video. God damn it. I'm good.
An app with your name on it just by thinking about it. Meet Base 44. In this video, we're going to talk about the basics
Of
of
NMR
NMR spectroscopy.
NMR spectroscopy.
NMR spectroscopy is useful for identifying the carbon-hydrogen framework of an organic compound. Now, it only works with certain nuclei, and that is nuclei either with an odd number of protons or an odd number of neutrons. So let me give you some examples. So nuclei such as hydrogen, carbon 13, nitrogen 15, fluorine 19, and phosphorus 31. These nuclei either have an odd number of protons or an odd number of neutrons, because as you can see, the mass number are all odd.
Oh, I forgot
And
the
the mass
names
number
for
is the
these.
sum of the protons and the neutrons.
Same element but different mass number. Ooh. What was it called? I forgot. Nucleophile? No. No, no, no. Oh, I gotta know that. If I don't know such a simple thing, I am so retarded. I'm sorry for using the word, but that is just normal. Isotope, yeah. Isobars and isotopes.
So let's take a look at carbon 13. So carbon 13 can work with NMR spectroscopy.
Where is
but
the
carbon
13?
12 cannot. Every atom of carbon has an atomic number of 6, and as you recall, the atomic number represents the number of protons. So carbon 13 has 6 protons and 7 neutrons. The mass number 13 is the sum of the protons and the neutrons. Carbon 12 has 6 protons and 6 neutrons. Carbon 12 does not have an odd number of protons, nor does it have an odd number of neutrons. So carbon 12 does not have a property called spin. Therefore, its nuclei will not be, you can't use it in NMR spectroscopy. Carbon 13 has an odd number of neutrons, so therefore you can use carbon 13 in NMR spectroscopy. Now, before we go into carbon 13 NMR, typically you'll learn proton NMR or HNMR. Now, hydrogen has a mass of 1. This is the most common form of hydrogen. There are isotopes of hydrogen like deuterium and tritium, but we're going to talk about this particular hydrogen atom. It has only 1 proton, no neutrons. So you can think of the hydrogen atom, or the hydrogen nuclei rather, as a proton. And a proton has a positive charge. And it has a property called spin. And if you study physics, you know that a moving charge creates its own magnetic field.
Yeah.
So you can think of the protons as generating their own magnetic field. Now, let's say if we have a sample of protons. So these protons, their magnetic field will have a random orientation. But what happens if we take these protons and put it in an applied magnetic field. What's going to happen? If we place them in an applied magnetic field, let's say it's going in the upward direction, we'll call it B naught. Then the magnetic fields of the protons, they could do one of two things. They can align with the external magnetic field,
or oppose,
or they can align against it. Whenever the nuclei are aligned with the applied magnetic field, this is known as the alpha spin state. And whenever they're aligned against the external magnetic field, this is known as the beta spin state. Now, as you can see, the alpha spin state is lower in energy than the beta spin state. And so the majority of the protons or the hydrogen nuclei
would be alpha.
will be in the alpha spin state.
Yep.
Because it's more stable. And what helps me to remember this is using the analogy of a river. It's easier to swim in the direction of the current rather than to go against it. So whenever the spin is aligned with the applied magnetic field, it's going to be in a more stable state. It's going to be lower in energy. It's going to be harder to go against the applied magnetic field. And so it takes more energy to do that. So thus, it's in a higher energy state.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone.
Now, delta E represents the difference in the energy of the alpha spin state and the beta spin state. Now, that difference in energy is dependent on the strength of the applied magnetic field. So as you increase the strength of the applied magnetic field,
the delta E is going to increase?
Will increase. And so you're going to have greater separation between these two lines.
Yeah.
Now, what does it take for a hydrogen nuclei to switch from the alpha spin state to the beta spin state? What you need is energy, particularly radio frequency energy. So if you add RF energy to a proton, and if it's the right amount of energy, it can flip from the alpha state to the beta state.
What?
Now, the beta state, a proton, if you add RF energy to...
What is RF energy? What?
A proton, and if it's the right amount of energy, it can flip from the alpha state to the beta state. Now, if the nuclei falls back from the beta state to the alpha state,
it releases energy.
It can emit radio frequency energy.
Radio frequency.
But it takes radio frequency energy to promote it from the alpha state to the beta state. And so when it's constantly flipping back and forth, it's in resonance. Thus we have the term nuclear magnetic resonance. So just remember that as you put energy into the hydrogen nuclei, you can promote it to the beta state. And as it falls back down, it's going to release energy. Now, if we want to, we can calculate the energy difference between the alpha state and the beta state. And here's the formula that we could use to do so. The energy difference is going to be Planck's constant times the frequency of the energy that we're going to use to put into the protons in the alpha state. Now, the frequency that we need is going to be equal to the gyromagnetic ratio divided by 2 pi times the strength of the applied magnetic field.
The fuck is that?
And so you can see that delta E, the energy difference between the two states, is proportional to the applied magnetic field. Now you might be wondering, what is gamma in this particular equation? So this represents the gyromagnetic ratio of the nucleus that you're dealing with. So in the case of the hydrogen nucleus, the gyromagnetic ratio is going to be 2.675
What?
times 10 to the 8 Tesla to the minus 1 times seconds to the minus 1. Now,
Per Tesla
for the
second?
carbon-13 nucleus, it's different. It's going to be 6.688 times 10 to
These
the
are
7.
constants you gotta learn.
And so it's less than that for hydrogen. So that's the formula you could use if you wish to calculate the energy difference between the alpha and the beta spin states. Now, sometimes you may need to calculate just the frequency that's needed given the strength of the applied magnetic field. And it's going to be the gyromagnetic ratio divided by 2 pi times the applied magnetic field. So you can also use this formula if needed. Now let's work on this problem. What is the operating frequency required of an H-NMR spectrometer that generates a magnetic field of 11.744 Tesla?
Magnetic field of...
To calculate the operating frequency, we need to use this formula. It looks like a V, but it's really the Greek symbol nu. So nu is equal to the gyromagnetic ratio divided by 2 pi times
E0,
the applied
V0.
magnetic field. Now, what is the gyromagnetic ratio in this case? Well, we can find the answer here. We're dealing with a proton NMR spectrometer. So for a hydrogen nucleus, it's going to be 2.675 times 10 to the 8. Now, the strength of the applied magnetic field is given to us in Tesla. And so that's 11.744 Tesla. And we need to divide it by 2 pi. When typing this in your calculator, make sure to put that in parentheses. So if you type in 2.675 times 10 to the 8, and then multiply that by 11.744, and then divide that by 2 pi in parentheses, you should get this answer.
500. Oh no.
At least that's what my calculator gave me. Now, we could round this answer and say it's approximately 500 million hertz.
Or 500.
Now, looking at our answer choices, we need to convert it to megahertz. If you recall, mega is 10 to the 6. So a frequency of 1 megahertz is 1 times 10 to the 6 hertz. So you want to set this up in such a way that these units will cancel. So 500 million divided by 1 times 10 to the 6, or 1 million, is 500. So the frequency is approximately 500 megahertz. So therefore, C is the right answer.
Okay. Oh no, that's not what I meant. Yeah. So NMR spectroscopy. So here they only talked about HNMR, which is for hydrogen. Does this belong to the hydrogen? Does these belongs to the hydrogen? Oh no, I don't know. I don't know. Come on. Now, what is NMR spectroscopy? Scopy. Scopy. What is NMR spectroscopy? NMR spectroscopy, nuclear magnetic resonance spectroscopy, is an analytical technique used to determine the structure of an organic compound by looking at the environment of certain atomic nuclei, most commonly hydrogen nuclei or carbon 13 nuclei. How does NMR work? Nuclei with spin, some atomic nuclei like H1H and 13C have a property called spin, which makes them behave like tiny magnets. External magnetic field: when you place a sample in a strong magnetic field, these spinning nuclei align with or against the field, creating different energy states. Radio frequency pulses: the sample is hit with the radio waves for specific frequency that can flip the nuclei from one energy state to another. Relaxation and signal: when the nuclei relax back to the lower energy state, they emit radio waves detected by the instrument. Chemical shift: the exact frequency at which the nuclei absorb depends on their chemical environment, nearby atoms, electrons. This causes shift in the resonance frequency called the chemical shift, measured in ppm, parts per million. What information does an NMR give? Number of signals shows how many different types of hydrogen environments, hydrogen or carbon environments are in the molecule. Chemical shift tells what kind of environment the proton or carbon is in. Splitting pattern multiplicity shows how many neighboring hydrogen there are. Spin coupling integration relative area under each peak shows how many protons contribute to that signal. Why is NMR important? It gives detailed information about the structure of organic molecules, how atoms are connected and arranged, used extensively in organic chemistry, biochemistry, and medicine. And MRA is based on NMR. So, nuclear resonance NMR, nuclear molecular resonance. What? Nuclear magnetic resonance. That is NMR. How do I make a short explaining NMR? Why is NMR important? Can explain how to interpret simple H-NMR spectrum step by step. Would you like that? How to determine the number of signals. I'll take this.
In this video, we're going to talk about how to determine the number of signals in an H&MR spectrum for a given molecule. So let's say if we have propyl bromide.
Let me see what this
How many
guy's
signals?
website has. It's taking some time. Connection timed out. There's something wrong with the server by this guy. Oh, whoa. Gotta be careful. Oh, there we go. That's Patreon. No, I don't have money to go Patreon. Practice problems. Okay. It's locked? I'll join.
Would you expect to have in an H&MR spectrum for this molecule? So what we need to do is determine the number of different types of hydrogen atoms that we have in this molecule. So let's consider the 3 hydrogen atoms in CH3. Will they show up as one signal, or will they show up as 3 separate signals? Now, each of these 3 hydrogen atoms, they have the same exact chemical environment. They are all attached to the same carbon atom, and they're all adjacent to this group. So those 3 hydrogen atoms are chemically equivalent, which means that in an H&MR spectrum, they will show up as just one signal. So generally speaking, the hydrogen atoms that are attached to a particular carbon atom usually show up as one signal. Not always, but usually. So we can call this signal A to correspond to those 3 hydrogen atoms. Now, these 2 hydrogen atoms are in a different chemical environment than these 3 because they're closer to the bromine atom. So they're going to show up as a different signal. And these 2 hydrogen atoms in the CH2, they're closest to the bromine atom. In fact, they're attached to the same carbon atom as the bromine atom. So they're going to show up as a different signal compared to the other hydrogen atoms. So for this particular molecule, we should expect 3 signals in the H-NMR spectrum. Now, let's try another example. Let's say if we have a molecule of propane, how many different signals would you expect to get from an H-NMR spectrum in this molecule? Now, what I like to do is draw a line of symmetry. Notice that the left side looks like the right side. When you see that, this tells us that the hydrogens in the methyl groups on the left and the right are equivalent. They're in the same chemical environment. Now, the CH2 hydrogens are different than the CH3 hydrogens, so we can call this signal B. So for this particular example, we should expect 2 different signals in the H-NMR spectrum. What about this example? Dimethyl ether. Once again, we can draw a line of symmetry in the middle. And so the methyl group on the left is identical to the methyl group on the right. So in this case, we are only going to get 1 signal for that molecule. Try this one. So how many signals should we get for this molecule? The first thing I like to do is identify the hydrogen atoms that are identical to each other. So looking at these 3 methyl groups, they are attached to the same carbon atom. And due to the free rotation of carbon-carbon single bonds, they are equally close to this group. So therefore, those 3 signals, those 3 methyl groups will show up as 1 signal. So we can call it signal A. They have the exact same chemical environment. Now, everything else is going to be different. This is going to be signal B, C, and D. As you can see, these 2 CH2 groups, they're not the same. They don't have the same chemical environment. This one is close to the quaternary carbon, and this one is further away, but it's adjacent to the methyl group. This one is not adjacent to the methyl group, so they're different. Thus, we should have a total of 4 different signals. Now, let's start using line structures in our examples. So let's say we have 3 bromopentane. How many different signals should we get in this molecule? So we could say that the line of symmetry is at the 3rd carbon.
2.
And we can call this
3.
signal A because
3.
they're equidistant from the line of symmetry. And the hydrogen atoms attached to those carbons, that's going to be signal B. And there's 1 hydrogen atom attached to this carbon, which will correspond to signal C. So this particular molecule is going to have 3 signals.
3
Try this one. 2-methylpentane. How many different signals should we get in this case? So here we have 2 methyl groups attached to this carbon. So those 2 methyl groups will
4.
be identical to each other. So that's going to be signal A.
4.
We do have
Or
a
5.
hydrogen atom attached to this tertiary carbon. And so that's going to be signal B. And
5.
then the rest are different. We really don't have a line of symmetry in this case. So all the other hydrogen atoms on the different carbon atoms will be different at the right side. Thus, we have a total of 5 signals for that molecule. Here's another one that we can work on. Try that one. So for this particular example, I'm going to draw the line of symmetry here, since
3.
we have a symmetrical molecule. Now, the hydrogen atoms on those two carbon atoms, they're equidistant from that
Oh,
line
this
of
might not be
symmetry.
3. This might
So
be
they're going to
2.
be identical. And then these two hydrogen atoms corresponding to signal B, they will be identical. Now, what about the methyl groups?
The
Are they
whole
identical
B.
to each other?
Yeah.
Should we say this would be signal C
Nope.
and this would be signal D? Or are all four of them identical to each other?
Yeah.
It's important to understand that these two are definitely identical to each other because we've covered examples like that before. But also, these two are identical to each other. They're equidistant from that line of symmetry.
Okay.
They have the same exact chemical environment.
Okay.
And so that's all four of them are identical to each other.
Okay. So it's 3.
So for this particular situation, we have a total of 3 different signals in the H&R spectrum. Now, what about this one? Now, I'm going to ask you 2 questions. How many signals should we get in the H-NMR spectrum? And how many should we get in the C-NMR spectrum? So let's focus on hydrogen. Now, we don't have a symmetrical molecule, so there's really no line of symmetry. Nevertheless, these 3 methyl groups are identical to each other. So in the HMR spectrum, they will show up as signal A. Now, these 2 methyl groups are identical to each other.
Identical B.
So they will show up as signal B. Now, we have a hydrogen atom on the tertiary carbon,
That's
so that's
C.
going to be signal C.
And
And
this
this
is
is
a 1D.
a CH2 group,
That's a D.
so that's going to be signal D. Now, this particular carbon has no hydrogen atoms. So in the HMR spectrum, we should only get 4 signals. Now, we do have a carbon atom here, so I'm going to use a different color. For the C-NMR spectrum, that's going to be basically signal E. So we should have a total of 5 signals in the carbon-13 NMR spectrum. Now, for the next example, we're going to use benzene.
Oh, fuck me, bro.
So how many signals should we get in the HMR spectrum of benzene?
2.
Now, it's important to understand that every carbon atom in benzene has 1 hydrogen atom. And all 6 of these hydrogen atoms are equivalent to each other.
Okay.
They
so
have the
that's
same
fine.
chemical environment. So this will show up as 1 signal. Now let's change it up a bit. So instead of benzene, let's say we have
Toluene.
bromobenzene. How many different signals should we get in the HMR spectrum?
2. 2.
And also, what about the carbon-13 NMR spectrum?
2?
So focusing on hydrogen,
2?
this will be signal A. We could draw the line of symmetry right at the center.
Oh, shit.
These 2 hydrogens, they're 1 carbon away from the bromine atom, so they have the same chemical environment. This would be
Okay,
signal
it's
B.
not 2. More than
They're
2.
2 units away from the carbon with the bromine atom. And
4.
this one is 3 units away, so that's going to be signal C.
4.
Now, let's focus on the carbon-13 spectrum.
That's 4.
So, the carbon atoms here are identical, just as the hydrogen atoms on them are identical. Now, these carbon atoms, they will correspond to signal B. They're identical too. And this one is different. Now, we do have a carbon atom here,
Yep.
but it doesn't have a hydrogen atom. So that will show up as the 4th signal in C-NMR. So in the H-NMR spectrum,
It's 3.
we have 3 different signals indicated
CNMR, it's 4.
using the red color. And in blue, for CNMR, we're going to have a total of 4 signals. A, B, C, and D. So be careful if you're dealing with C NMR or H NMR. If you have a test, make sure you pay attention to this because it can affect your answer. As you can see, the number of signals for these two different spectrums can be different. Now let's work on para-xylene as an example. And we're going to focus on both H NMR and C NMR. So how many H NMR signals should we get for this molecule? So let's identify all of the hydrogen atoms first.
3 is HNMR. For
And let's
CNMR,
also
it's going to
identify
be
the line
4.
of symmetry, which is here.
No, that's
So
still
these
3.
two will show up as signal A. Now notice that these 4 hydrogen atoms, they all have the same chemical environment.
Yeah. So
These two are
two?
identical to each other.
2?
And at the same
Okay.
time,
Okay.
these two are identical to each other. They're 1 unit away from the methyl group. And these two are also 1 unit away from this methyl group.
So it's B.
So all 4 of those hydrogen atoms are identical to each other. They show up as one signal. So thus we have a total of 2 different signals in the HNMR spectrum. Now for CNMR, I'm going to use the color green. These two will show up as one signal. Now these 4 carbon atoms, they're identical to each other.
B.
So that's going to be signal B.
And the one...
Now these 2
Yeah.
carbon atoms, which do not have hydrogen atoms,
both will be C.
they are identical to each other. So for CNMR, we're going to have 3 signals as opposed to 2. Now let's try ethylbenzene for the next example. Go ahead and work on that example. So let's draw the hydrogen atoms. Now, on the ring, the line of symmetry will be right in the middle. So these 2 hydrogen atoms are identical to each other. These 2 are identical to each other, but they're different from this one. These are not the same because hydrogen A is 1 unit away from the ethyl group, but hydrogen B is about 2 units away from it. This we can call hydrogen C, and D and E, because we do have hydrogen atoms on these 2 carbon atoms. So in the HNMR spectrum, we should have a total of 5 signals. Now for CNMR, everything is going to be the same, but we do have this carbon atom that doesn't have a hydrogen atom. So that will correspond to signal F in the CNMR spectrum. So we should have a total of 6 for CNMR. Now what about this one? Meta-dichlorobenzene. Try that.
Whoa, wait,
So let's begin by drawing.
It's gonna be symmetric here. No, I think it's gonna be symmetric here. And 1, 2, 3. So HNMR is 3 and CNMR is 4.
The hydrogen atoms. Now, where is the line of symmetry?
Between
I
the
would say
chlorine.
the line of symmetry is here,
Yep.
between the 2 chlorine atoms. And we can see that these are identical. They're symmetric across the line of symmetry. So this is going to be signal A for HNMR. These 2, signal B.
That one C.
And then this one is going to be signal C. So we should expect 3 signals in the HNMR spectrum. Now for CNMR, let's use a different color. We focus on the carbon atoms, so that's going to be signal A. Here, we're going to have
B.
signal B. And then for these 2 carbon atoms, that's going to be signal C.
And
And for this one, D. So for CNMR,
It's
it's
4.
going to be one more than HNMR due to these two carbon atoms which don't have hydrogen atoms on it. Now let's work on a different example, one that doesn't involve benzene rings. So how many different signals should we expect in the HMR spectrum for that molecule?
1,
What would you say?
2. 2.
So these two methyl groups, are they identical? Now remember, if you have a carbon-carbon double bond, there's no free rotation. So those two methyl groups are identical. They have the same exact chemical environment. This methyl group here is cis to a hydrogen atom, and it's also trans to a hydrogen atom, and it's attached to a carbon that has a methyl group. The same situation applies to this one. It's cis to this hydrogen, trans to that one, and it's attached to a carbon with another methyl group. So they have the same chemical environment. Now, these two hydrogen atoms, they also share the same chemical environment. So that will be signal B. So thus, we should get 2 signals for this particular molecule. How many signals will there be for this molecule? So we only need to focus on these 2 hydrogen atoms.
1.
Are they identical or are they different?
Identical.
So this hydrogen is cis to a chlorine atom, and it's trans to a hydrogen atom, and it's attached to a carbon atom with another chlorine atom.
One
the same
signal.
is true for the other one. It's cis to that chlorine atom, trans to a hydrogen, and it's attached to a carbon with a chlorine atom. So therefore, they're identical. Thus, we're only going to have 1 signal for that molecule. Now, let's try one more example.
Okay.
How many different signals should we get in the HNMR spectrum for this molecule?
1.
So let's compare
Wait. These would be equal. So 1, 2, 3.
2 hydrogen atoms first. Are they identical or are they different? Now, this hydrogen...
Oh, no, I don't think okay, it's gonna be different, right? So, 1, 2, 3, 4, 4.
is cis to the CH2Br group. This one is trans to it, so automatically they're different from each other. Now, this hydrogen is going to be different from any one of these two because it's on a different carbon. It's on the same carbon as this group, whereas these 2 hydrogen atoms are on a different carbon than this group. So automatically, this is going to be a different hydrogen atom. Now, these 2 hydrogen atoms are different from the rest because they are attached to a carbon atom that is directly connected to the bromine atom, whereas all of the other hydrogen atoms are attached to a carbon that does not contain the bromine atom. So this will be signal D. Thus, for H NMR, we should expect 4 different signals. Now, for C NMR, this carbon is different from that carbon because the first carbon has 2 hydrogen atoms attached to it. The second one only has 1. Now, the third one has 2 hydrogen atoms attached to it, but it's the only one with the bromine atom. So, in the case of CNMR, we should only get 3 signals. So that's it for this video. Now you know how to determine the number of signals in an HNMR spectrum and also in a CNMR spectrum. So if you like this video, feel free to subscribe, and thanks again for watching.
Not the ads. I think I should take a shower. So people. Or should I? Or should I take a shower? I don't know. I feel like I should take one, but I'm just too tired to do that. Okay. What else? What else? What should
Mach dir keine
fucking
Sorgen.
ads,
Der
bro?
vertrauensbeste Bodytrimmer. Für eine ultimativ sanfte und komfortable Rasur. Selbst an sensiblen Stellen. Entdecke jetzt den Braun Body Groomer 7.
Aufgepasst! Eingebranntes Essen ohne Vorspülen? Mit Fairy kein Problem. Probier's aus.
Fairy Platinum Plus Spülmaschine-Tabs kombinieren Pulver zum Entkrusten.
The fuck are these ads? 20 minutes? 20 seconds?
Hartnäckige Essensrückstände.
What
und
the
sagt
hell?
strahlenden Glanz. Fairy Platinum Plus. Unsere besten Tabs für die Spülmaschine.
In this
But
video,
hey, I forgot. These creators are getting paid, so I don't care.
we're going to talk about chemical shift. Chemical shift, represented by the symbol delta, is basically the ratio of the observed chemical shift, which is typically given in hertz, divided by the operating frequency of the spectrophotometer, which is typically given in megahertz. Now, to get a number between 0 and 12, you're going to have to multiply this by 10 to the 6.
0, 0, 0, 0.
Now, on the x-axis, these represent chemical shift values for different signals. And the units is ppm, parts per million. Now, what we have here is a reference signal, TMS, also known as tetramethylsilane. It's basically a silicon atom with 4
Metal groups.
On the right, we have methyl bromide. Now, notice that methyl bromide has a higher chemical shift than TMS. The reason for that is because bromine is more electronegative than silicon. Because the protons are next to an electron withdrawn group, they will have a higher chemical shift. Thus, they will appear downfield on the NMR spectrum, which is basically the left side. Upfield is towards the right side. The protons that are shielded to an external magnetic field, they will appear upfield. The ones that are de-shielded will appear downfield, which is due to the presence of an electron withdrawing group. So here's a question for you. Let's compare methyl bromide with methyl chloride. So dealing with HNMR, which one will have a higher chemical shift? Would you say it's the protons in methyl bromide or the protons in methyl chloride? Because bromine is more electronegative than chlorine, methyl bromide should have a higher chemical shift than methyl chloride. So when dealing with the halogens, here's what you need to know. So methyl fluoride is going to have the highest chemical shift. Then it's going to be methyl chloride, followed by methyl bromide, followed by methyl iodide. So this is due to the inductive effect. So the proton that's attached to a carbon with a more electronegative atom attached to it is going to have the higher chemical shift. It's going to appear more downfield. Now, according to one textbook, here are the values for these compounds. So the chemical shift for methyl fluoride, that is the protons on it, it's about 4.3 ppm, or parts per million. For methyl chloride, it's 3.1. For methyl bromide, it's about 2.7. And for methyl iodide, 2.2. Now for methane, if you want to compare that to methyl iodide, it's much less. It's going to be about 1.0 ppm. So the presence of a halogen will greatly increase the chemical shift of these compounds. Now the next thing that we need to mention, which is obvious in nature, but it's good to see it, is that if the number of electron withdrawing groups increases, the chemical shift will increase as well. So in this example, we have 3 chlorine atoms, and the chemical shift for this proton is 7.3 ppm. Now we're going to compare it if we had
No, I did
2
not hear
protons.
anything. I'm sorry.
Methyl chloride with methyl chloride will appear downfield, which is due to the presence of an electron withdrawing group. So here's a question for you. Let's compare methyl bromide with methyl chloride. So dealing with HNMR, which one will have a higher chemical shift? Would you say it's the protons in methyl bromide or the protons in methyl chloride? Because bromine is more electronegative than chlorine, methyl bromide should have a higher chemical shift than methyl chloride. So when dealing with the halogens, here's what you need to know. So methyl fluoride is going to have the highest chemical shift. Then it's going to be methyl chloride, followed by methyl bromide, followed by methyl iodide. So this is due to the inductive effect. So the proton that's attached to a carbon with a more electronegative atom attached to it is going to have the higher chemical shift. It's going to appear more downfield. Now, according to one textbook, here are the values for these compounds. So the chemical shift for methyl fluoride, that is the protons on it, it's about 4.3 ppm, or parts per million. For methyl chloride, it's 3.1. For methyl bromide, it's about 2.7. And for methyl iodide, 2.2.
2.2, this
methane,
would be methyl
If you want to
iodide.
compare that to methyl iodide, it's much less. It's going to be about 1.0 ppm. So the presence of a halogen will greatly increase the chemical shift of these compounds. Now the next thing that we need to mention, which is obvious in nature, but it's good to see it, is that if the number of electron withdrawing groups increases, the chemical shift will increase as well. So in this example, we have 3 chlorine atoms, and the chemical shift for this proton is 7.3 ppm. Now we're going to compare it if we had 2 protons on this carbon instead of 3. So the chemical shift for dichloromethane is about 5.3 ppm. And then let's compare that to methyl chloride, which we said was 3.1, and methane, which is about 1 ppm. So as you can see, the more halogens or the more electron withdrawing groups that you have on a carbon atom, it's going to basically pull the electrons from the carbon atom, thus making this proton de-shielded towards an external magnetic field, thus increasing the chemical shift of that proton on an NMR spectrum. Now the next thing we need to talk about is
What the hell?
NMR spectrum. The chemical shift of that proton on an NMR spectrum. Now the next thing we need to talk about is the position of the protons relative to an electron withdrawing group
Imagine being able to build anything just by thinking about it. Meet Base
No.
44.
I don't imagine. Dude, I'm gonna end the YouTube stream for now. I gotta take a shower. I need to ease my mind. It's a lot of information, you know. My stupid brain needs some rest, I guess. You know, we will get better. I know I should be sitting here and I need to focus a long time, but right now I'm gonna take a rest because I don't know if it's what is it? Is it ADHD or autism? One of these. I do have one of these, maybe. Peace.